So let's talk about reacting gas equilibrium. We started setting this up last time, and now we're going to derive the key equation. So we're going to equilibrate. It's really hard to say the word equilibrate while writing the word equilibrium. I somehow got that right. Gas phase reaction at equilibrium at fixed T and P. So we mix gases and we let them react. We're going to do this in general terms. Reaction A plus B goes to 2C. And of course, everything we're going to do is general. Doesn't have to be for a reaction of this form. Okay. So we know that the condition of equilibrium at fixed temperature and pressure is that the Gibbs energy is at an extremum. And so we care about its differential. So let's use what we know. Okay, so here we have the total differential of the Gibbs free energy for changes of temperature, changes of pressure, and changes of mole number. And again, the independent variables for Gibbs are temperature, pressure, and mole number. You can see that right here in the differential form. And why do we choose that free energy? Why do we choose Gibbs? Why is this convenient? Because we can ignore 2/3 of the right-hand side of the equation. For fixed temperature and pressure, right? Those are fixed. Fixed and stubborn and independent are like synonymous in thermo, right? If they're independent, that means they can be stubborn and not move. So those go to 0, and we care only about this term. So we're going to be spending the lecture analyzing that term. And so equilibrium is determined by the chem potentials UI and the mole numbers. So that's going to be it. Our entropy and our volume are not going to be explicitly part of this. Oh. I like it better. All right. So at equilibrium, dG equals no, that's the equilibrium expression. So all that. How many independent variables are there in this case? I'll remind you, we have a general reaction, A plus B goes to 2C. That's a reaction. Let me break that down a little bit. Somebody tell me, what are the components? Let's list the components. Yeah, those are the I labels, components I. What are the components in the system?
A, B, and C.
Components are A, B, and C, right? So this label runs over A, B, and C. Okay. So we have 3 mole numbers, N of A, N of B, and N of C. How many independent variables do we have? This is carried from the previous lecture.
Like 5.
5. How do you get 5?
number of components and then two independent variables for thermodynamics?
So I see you're taking the numbers 3 and 2, but you're adding them, and then you should be subtracting them. And the reason is the following. We have 3 components. We have 3 NIs, right? But reaction balance means there's only 1 degree of freedom. How do we know that? Because we have 2 constraints. What are they? dn of A over nu of A equals dn of B. Remember this from last time? d nu of B equals dn of C over nu of C. There's 2 independent equations in here. You can count the equal signs. There are 2 equal signs. So we have 3 components, but 2 constraints, which means there's only 1 degree of freedom. And we introduced this reaction extent equals dC. You don't have to use C to answer any problem you're going to find in this class, but it is a nice general form. Okay, so we have, for one reaction, univariant, it could be called, we have only 1 degree of freedom. All right, so now we're going to solve the reaction equilibrium condition by applying those constraints. So apply constraints. And here, I'm going to arbitrarily choose the product mole number as the independent variable. So let's see, we have dn of A equals nu of A over nu of C, dn of C equals minus 1/2 dn of C. dn of B equals nu B over nu C, dn of C equals minus 1/2 dn of C. Again, this sort of makes sense. A plus B going to C. For every mole of C that's created, sorry, 2C, I apologize. For every 2 moles of C that are created, there's 1 mole of A and 1 mole of B that are destroyed. So it works out, right? For every 2 moles of C are created, you destroy 1 each mole of A and B. Okay. So what I'm going to do is I'm going to plug these into my expression for dg. dg equals, again, repeating from the previous board, mu of I, dn of I, and now I'm going to eliminate dn of E, A, and dn of B, and write everything in terms of dn of C, and you get the following. Mu of A over nu of C, plus mu of B, nu of B over nu of C, plus mu of C. And here is my equilibrium condition. Okay. Now this should have a certain kind of similarity to what we did with the case of unary systems when we derived the equilibrium condition for 2-phase coexistence. We had a chemical, we had an entropy, I think, in that case, on the left-hand side. And we needed it to be at an extremum or optimized. That is, its differential being 0. Right. So we have 1 independent variable here, dn of C. I'll write down some points here. dNc is unconstrained. It's unconstrained. We can't assume that this is 0. Why is that? Why can't we assume that's 0? We call this an unconstrained internal variable. Why is it unconstrained?
Because even at equilibrium, the reaction doesn't stop.
Right. So we can constrain pressure. We have pressure gauges and pressure regulators, right? Those exist. You can buy them. We can constrain temperature. We have thermostats, right? Those exist. You can buy them. And you can think of different experimental setups to constrain the temperature and constrain the pressure. However, I want you to think of a box of gas, and you have molecules of A, B, and C, and they're zooming around in here. And this reaction can take place, right? You can't stop it. So even at equilibrium, this is going to fluctuate. The reaction is going to run a little to the right, a little to the left. And if you're away from equilibrium, the reaction will definitely either run to the right or to the left, right, depending. That's the meaning of unconstrained. You can't fix it, right? You can't go in there with your atomic tweezers and stop the atoms from reacting. That's an important concept. So if we have, and this is rather like the case in the unary two-phase system, when we had a phase boundary and we couldn't stop the phase boundary from fluctuating, right? We couldn't stop a little bit of solid from evaporating, for instance, or a little bit of gas from condensing. That would be an equivalent example. The math worked out in a very similar way. So if we need this expression to be 0, and this in general is non-zero, how do we enforce equilibrium?
Do we have to assume that the coefficient is 0 then, since
Coefficient.
is 0?
Thank you. I didn't see who said that, but that's exactly right. If you have a function, you're optimizing it. Here I draw for a maximum, same thing for a minimum. How do you enforce the condition of being optimized? You make the slope 0, right? That's what we're doing here. Coefficient, the coefficient dg dnc must be 0 at equilibrium. That becomes the equilibrium condition. Right. So there's some calculus in here. There's some, in this case, one-dimensional function optimization in here. That's calculus. And then there's also some science, right? You have to recognize that this reaction is going to happen. You're not going to stop it. And so if DNC can't be enforced to be 0, then you've got to call this thing equals to 0, the equilibrium condition. So there's a lot in here. There's a lot to unpack. All right. So, all right. Now, fortunately, we have expressions for those chemical potentials. So we're going to substitute ideal gas mixture expressions. This is from last time. For the mu i's. We have expressions for the mu i's from last time. So I'm going to substitute those in. And I get the following. dg equals mu A naught, that is component A in its reference state, pure at 1 atmosphere, plus RT, natural log, partial pressure of A over standard pressure. This quantity times mu A over mu C plus mu B naught plus RT, natural log, partial pressure B over standard pressure, nu B over nu C plus mu C naught plus RT, natural log, pressure of C over standard pressure. This whole thing times dN of C equals 0. And as a reminder, mu I of naught equals the reference or standard chem potential of component A, not A, I should say component I, at pressure P naught and temp T. And for P naught, we almost always choose 1 atmosphere. Okay, so we substitute. Now we're going to collect terms. Collect terms and multiply through by nu of C. I'm going to get the following. Nu of A, mu A naught, plus nu of B, mu B naught, plus nu of C, mu C naught. I group these, plus RT, natural log, P of A over P naught to the power nu A, P of B over P naught to the power mu B, P of C over P naught to the power mu of C equals 0. Just manipulating the thing which we wrote down previously. Okay, we're going to continue to simplify this. We're going to define something. Define delta G naught equals this thing in parentheses. Equals the sum over I of the nu of I times the reference potentials. Why does that make sense to define it that way? In this case, it's the following. 2 mu of C naught minus mu of A naught minus mu of B naught. Recalling again what our reaction is, it's A plus B going to 2C. So what is this thing? It's the free energy change of the reaction when all components are in their standard state. So for instance, if we assume that our standard pressure is 1 atmosphere, if you take 1 atmosphere of A and you react it with 1 atmosphere of B, and you produce C, where C is also 1 atmosphere, the change in Gibbs free energy is this delta G naught. And that doesn't have to ever correspond to a physically practical reaction. Right? You might not ever realize that particular reaction in the lab. But thermo is all about state functions and reference data. And we're picking convenient reference data. And you can imagine that reaction even if you don't carry it out. That is, one atmosphere of A, one atmosphere of B, and one atmosphere of C at equilibrium. Okay, so you will find these delta G, one second, sorry. You will find these delta G naughts in databases. That's the sort of thing you're going to find. If you're trying to engineer something and you need to design a reactor, you're going to be looking at these delta G naughts and going forward from there.
Yeah, sorry, I just had a quick question. Are all those partial pressures in the natural log?
Yes, they're all in the natural log. That's a
Okay.
natural log.
Yeah.
Let me make that really explicit. Does that help?
Yeah, thanks.
Yeah, and that just comes from the properties of natural logs. You know, natural log x plus natural log y equals natural log xy. So we just applied that sum product rule multiple times. Okay, let me continue simplifying. We're simplifying. I was just at Walden Pond with my kids over the weekend. I think that was Thoreau who said sort of above all simplify. It's like he was describing what someone should do in Mathematica. So we're going to define this thing called the equilibrium constant, which some of you may have encountered in other classes, but here we've derived it. K of P equals product operator over components P of I, partial pressure normalized to standard pressure to the power of nu of I. So that is the equilibrium constant in terms of the pressures. That's K sub P. Okay, so that's kind of a big deal because this shows up in all over the place, including in some introductory chemistry classes. All right, we're going to further simplify. Simplify by assuming that total pressure, we're simplifying here, but the total pressure is the reference pressure, so that P of I over P naught equals X of I, making that even simpler, again using Dalton's rule. And if we make that simplification, we get a cleaner expression for the equilibrium constant, which is the one that we're going to use most often in this class. And for this reaction, again, for the reaction of A plus B going to 2C, this equilibrium constant is the mole fraction of C squared over the mole fraction of A and mole fraction of B. Okay. So one more simplification, and then I'm going to stop and ask for questions. We're going to collect terms. To write concise expression for reaction equilibrium constant. And this is the sort of expression that you may have been given in a chemistry class, or you might find in Wikipedia, or Kp equals E minus delta G naught over RT. Okay, so this is our final answer. This is what we're going to, this is what's going to be useful for you, right, after this class, when you're analyzing reacting gas systems. But now you've seen it derived and you know where it comes from. I want to pause now. I went through that basically without interruption, or hardly without interruption. So I want to pause and take questions. At Walden Pond, I saw a great demonstration of thermal. There was one person out on the ice. This is on Saturday. I mean, it was warm. And one person was out on the ice, and everyone who wasn't on the ice was watching this person. And the ice was it was sunny, and they fell through. So it was thermo in action. I saw someone fall through the ice. They were fine. I think every people were laughing at them. It wasn't very deep where they were. And they struggled back onto the shore with their friends, and I'm sure were laughed at for the rest of the day. So there's thermodynamics in action at Walden Pond. I don't have a picture to share with you though. All right, questions on how we got this, because we're going to be using this a lot.
Yeah, I have a question about the mole fractions. Are those like, I guess, where did the mole fractions come from? Are they the mole fractions that the components find themselves in at equilibrium?
Right. So first of all, let me answer your question in two parts. First of all, this is Dalton's rule, right? It's the definition of partial pressures almost, right? So that's Dalton's rule. What mole fractions are we talking about here, right? That's a great point. So we're not going to do this a whole bunch in this class, but you're set up to do this. Let's imagine non-equilibrium and equilibrium. Non-equilibrium, there's something called, sometimes it's written as reaction quotient, sometimes it's written as reaction constant. It has different forms, but it's written, it's the exact same thing as a reaction constant. But in general, it's not equal to its equilibrium value. In general, it's not equal to its equilibrium value. So let's see what that means. Say that Q is greater than K sub P. Right, so the numerator is too large or the denominator is too small relative to equilibrium, right? So if the numerator is too large or the denominator is too small relative to equilibrium, what direction will the reaction run? And we can answer the question thinking specifically about this case.
Would it go to the left towards the reactants?
Right. Let's look at this. If this thing is too big relative to equilibrium, that means there's too much C or there's not enough A times B. Sorry, I was really messy there. That's X of A. So what that's telling you is that you're out of equilibrium and you're out of equilibrium to the right. And the reaction will run spontaneously to the left. And the math works out. You will find in this situation that running to the left decreases the Gibbs free energy. In other words, dg dn of C. What's our situation here? Let me try to draw that. We have, this is a situation where Gibbs free energy versus n of C, you want to run to the left to decrease Gibbs. So you have a curve like that, right? You run to the left to decrease Gibbs. The math will all work out. I know I'm being qualitative here. dg dn of C is greater than 0, positive slope. And so it's telling you the reaction will run to the left. And the difference between the reaction quotient and the equilibrium constant, that can be called reaction affinity or driving force. And there's all sorts of analyses of this. And it couples to rate, and there's a lot of engineering in here, right? You want to figure out if you want to design a reactor, how far away from equilibrium should you design it to be, stuff like that. On the contrary, right? Let's say Q is less than K of P. I mean, it's going to be the opposite. This is a case where there's not enough numerator, there's too much denominator, right? The quotient is small, smaller than equilibrium. So this is a case where you're going to decrease Gibbs energy by going to the right. dn of C less than 0, and the reaction will drive to the right. At equilibrium, right? At equilibrium, N of C, G, right? They're right there, where the Gibbs free energy is minimized. So you can write down this expression out of equilibrium, right? And you might, and compare this to this expression, which you get from the thermodynamics of the reaction, and determine whether your reaction will run spontaneously to the right or to the left, or is it actually at equilibrium? Did that help answer your question? I'm not sure.
Yeah, that made sense. Thank you.
So you can basically, you can evaluate this instantaneously. Whether or not it's equilibrium depends, right? But you can always sort of write that thing down. And again, we're not doing really, we don't really have the time in this class to talk about a bunch of out of equilibrium reactions and talk about rates and affinities and stuff, but that will come later in course 3 and other courses, right? And so you're sort of well set up because we understand equilibrium, we can start analyzing, you know, out of equilibrium situations. And non-equilibrium thermo exists. It's a fascinating topic, I think. And I teach it as part of the advanced thermo class, but we have no time for it here. Other questions? I'd like to make sure that people, this is a point from last lecture, but I'd like to make sure that people understand how we get this numerator denominator thing out of this expression. Right? Remember, the reaction coefficients are positive for products and negative for reactants. So products end up with a positive power, and reactants end up in the basement here with a negative power. So, you know, often if you've seen this before, let's say in introductory chemistry, you were probably told just to put products on the top and reactants on the bottom. Well, this is where that comes from. Right? So it's good to know it comes from somewhere. Maybe everyone understood that. I don't know, but worth mentioning. So on the P set, you're asked to evaluate the equilibrium condition for a couple of reactions. And that often boils down to finding the delta G's. So I want to make this really explicit here before moving on. Delta G's, delta G naught equals G naught products minus G naught reactants. Right, so that's right, G naught products at some temperature, let's say T2, equals G naught products at T1 plus some integrals. I mean, we've done those integrals already. We know how to do those integrals. For instance, you integrate entropy or temperature or something like that. G naught reactants at some temperature 2 equals G naught reactants at some temperature 1 plus integrals. So we're seeing that delta G naught at some T2 equals delta G naught at some T1 plus integrals. And these depend on the heat capacity differences. So I'm doing this at a very high level and quickly here because I want to highlight the similarity to the case of the unary transformations. We had in unary systems, we had transformations between phases, and we could analyze things like the change of Gibbs free energy or any other state function, change of H or change of S across that transformation. And we could calculate the temperature dependence of that by integrating things that depended on heat capacity differences. It's all formally the same right now. We're having a transformation from reactants to products. The delta G naught is important. That helps us determine equilibrium condition. And in general, it's temperature dependent. And you're going to find things like delta G naughts or their equivalents tabulated at standard temperatures in databases. And you might be asked to calculate reaction balance at some other temperature. And to do that, you're going to need the CPs and the delta CPs. So formally, it's very similar to the unary case. I wanted to highlight that. All right,
And
so-
if a problem is just happening at standard temperature, can you then just use the standard Gibbs values? And I guess you
Yep.
wouldn't need it to integrate in that case?
Yes, indeed. Yep. H naught for elements at standard temperature and pressure is defined as 0. S naught for elements at standard temperature and pressure is a number, often in the back of the Hoff. Delta H naught, delta S naught, delta G naught for compounds. Those are numbers often found in the back of the Hoff for common reactions. That's right. And so if you're at standard temperature and pressure, you normally have everything you need, even in Wikipedia, for standard reactions. And you know, we're analyzing like ammonia in this, you know, so it's very common substances, easy to find the data. Thank you for that. All right, let me move on. Risk of repeating myself. Notes on reaction equilibrium. Okay. A negative delta G naught drives reaction to the right. That's sort of a straightforward point. Adding more of a given component shifts reaction balance. It shifts the reaction balance to maintain equilibrium. That's LeChatelier again. Any change in the status quo prompts an opposing reaction in the responding system. And one more thing. For 3 or more components, there's no unique equilibrium condition. So let's analyze again this case, x of c squared, x of a, x of b. And this equals, okay, so this thing here is just a number, let's say at a given temperature. It's a number, and we have 3 variables. We know that x of a plus x of b plus x of c equals 1 by definition, right? They're mole fractions. We still have 1 degree of freedom at equilibrium. So there's an infinite number of compositions that would satisfy equilibrium here. You can play with the math. If you want to parameterize, you know, you can fix x of c and then calculate x of a as a function of x and b here, if you like. There's lots of ways to sort of slice this, but basically, you could shift your equilibrium balance. So how does that work? Let's see how this works with the Chatelier. Let's say you're at equilibrium. And you add a little bit of more x of b. You inject a little bit more component b into your system. So the denominator ticked up a little bit. How's the reaction going to respond? How's the reaction going to respond? We just added a little bit more of b. We kicked it out of equilibrium. How will the reaction respond?
It'll flow to the right to make more C.
Yeah, it's going to swerve to the right to try to counteract that change and bring this expression back to equilibrium. So you add more b, the reaction shifts to the right. Likewise, if you add more c, the reaction will shift to the left. If you take away some a, the reaction will shift to the left, and so forth and so on. You cannot get away from the Chatelier. It's always going to be there, trying to restore equilibrium. It's in the math. I know it bears pointing out from time to time. All right, let's talk about temperature dependence. This gets to one of the problems in the homework. Temperature dependence of reaction equilibrium. I'm just going to do some math here and we'll talk about the meaning. Let's calculate the partial with temperature at fixed pressure of reaction balance. And I'll do log of K of P because the math is easier this way. This is d dt at fixed pressure of minus delta G naught over RT. Okay. And by chain rule, this equals delta H naught over RT squared minus 1 over RT d delta H naught dt at fixed pressure plus 1 over R d delta S naught dt at fixed pressure. So that's just the chain rule. D delta H naught over dt at fixed pressure equals delta Cp. Again, coming back to transformation quantities. And d delta S naught dt at fixed pressure equals delta Cp over T. We're relying on this a lot. And you might want to remind yourself of this. You might want to show this just in the minutes after class. You can go back to when we introduce these potentials. So using these expressions, we find d log a K of P dt at fixed pressure equals delta H naught over RT squared. And this has a name. This is called the Van Hoff equation. Okay, you're going to use a form of this in the homework because you are implicitly asked to calculate how the reaction balance changes with temperature. Let's see how this works out. Let's see how the math works. So for example, let's consider an endothermic reaction. Endothermic reaction, Q and delta H naught are greater than 0, right? That's an endothermic reaction. For example, that's the cold pack, right? Sorry, instant cold pack. Delta H equals reversible heat for the reaction. Delta H greater than 0 means d log Kp dt pressure is greater than 0. what does that mean? Reaction moves to the right or left with increasing temperature? With increasing temperature, do I move to the right or the left if this condition is true?
To the right.
Move to the right, right? K of P is products over reactants. So if K of P is increasing, if this slope is positive, that means I'm moving to the right. Reaction moves to the right with increasing temperature. What does that mean? The system tries, right? Doesn't actually know what it's doing, to oppose the temp rise by taking up heat in an endothermic reaction. If you try to raise the temperature, it's going cold pack on you. That's what Hoff says. You cannot get away from the Chatelier. And the converse, of course, is going to happen for an exothermic reaction. Let me ask you, if I just wrote that backwards, right? Products, I just flip it, make products reactants and reactants products. Everything I just said would be, have a sign flipped. And it works out. Because nature doesn't know how I wrote this. Nature doesn't care how I wrote this, right? It doesn't know what the difference between products and reactants are. So an exothermic reaction moves to the left with increasing temp. Right, okay.